So before we get into the formulas for our binomial distribution, which you see on the screen, let me first point out to you some variable notation we're going to be using. Remember, we said that in order to meet the criteria for a binomial probability distribution, we have to have a fixed number of trials. And we were sort of noticing from the previous examples that that fixed number of trials was really just our sample size. So recall that we are letting the lowercase letter n represent the sample size. X is always going to represent the number of successes from our trials we're looking at. So whatever the question is we're looking at would be the variable that's changing, and we're going to let that be represented by X. And the number of successes that we can get is going to range anywhere between 0 successes all the way up to and including n successes, which would be successes for 100% success, if you will. Lowercase p is another p that we're going to see used in the course as opposed to capital P, which is probability. Lowercase p is the probability of our success for our trials, whereas 1 minus p then would have to be the probability of failure, because remember that probability has to add up to be equal to 1 or 100%. So if we have only 2 outcomes, probability of success is p, 1 minus p has to be the probability of failure. And then the other thing that I would point out to you here on the screen is this orange caution box. The part I have highlighted here says that when you're sampling without replacement, similar to that example we saw a moment ago where we were talking about picking 4 committee members out of a hat from 19 Republican and Democrats together. If I pull a name out of the hat and put it off to the side, and then I go back and I draw another name out of the hat, that's considered sampling without replacement because I didn't put the name back into the hat I had originally drawn. When we are sampling without replacement, we just have to make sure that our sample size n is less than 5% of the population, capital N. If that's the case, then we can go ahead and just assume that we have independence if that criteria is met. More often than not, that criteria is indeed met, that your sample size is less than 5% of your population, but now we have some sort of mathematical formula to numerically show, sure enough, I can check that my samples are independent, that my experiments are independent of each other. So that's a little bit of a notation, information about the notation. Now let's talk about our distribution formulas. So here you see, in order to calculate the mean of my variable I'm interested in, so that's what mu sub x is standing for. This is the mean. We haven't seen mu in a while. This is saying the mean of my variable x is equal to the sample size times the probability of success. So n times p. And then we will be calculating both mean and standard deviation in this case. Standard deviation of our variable x can be found by taking take the square root of all of this stuff underneath that radical sign. So I would take n times p times 1 minus p, multiply all of those things together first, and then take the square root of it, and you have the standard deviation. And then finally, before we move into our example, just remember that you need to be aware of how to change these phrases into their corresponding mathematical symbols. So at least, no less than, greater than or equal to, obviously mean the symbol greater than or equal to, and so forth. So you've got your phrases here in words and their equivalent math symbols over here on the right.